Nicholas Leonard Sadie Carnot. Does his name ring a bell? I'll give you a clue. Ice melting, hot pans cooling down. Any ideas? It's a concept that's crucial in chemistry and helps explain why physical processes go one way and not the other. Why warm drinks get colder and not hotter. Well, the second law of thermodynamics can help us understand how reactions can be spontaneous, stating any spontaneous process increases the disorder of the universe. In terms applicable to chemistry, this is known as entropy. Entropy is a measure of molecular randomness or disorder. Think of it like this. Entropy is the number of ways each energy configuration can be arranged within a system. There are many ways that energy can be distributed within a system and still have the same total energy. These different configurations are known as microstates. If a single configuration has more microstates, then there's a higher probability of it occurring. Within these arrangements, the configuration with the energy most dispersed has the highest entropy. So, think of entropy as the measurement of energy spread. So, is it even useful? Yes, entropy tells you about the feasibility of a reaction and how the energy is being degraded. Whenever entropy is generated, there's a deviation from the ideal process, representing a degradation in the quality of the energy. This shows us the loss in the potential to extract useful work out of some of the energy. So whenever we carry out processes, we try to limit the entropy generation, although this can never be avoided. Tying in well with thermodynamics are spontaneous reactions. But what does it mean for a reaction to be spontaneous? In chemistry, spontaneous doesn't refer to how fast something happens, but means a process that doesn't require external energy to keep going. And that's exactly what a spontaneous reaction is. Gibbs's free energy relates enthalpy, entropy, and temperature. For spontaneous reactions, delta G must be negative. The change in standard Gibbs free energy for a reaction is equal to the change in standard enthalpy minus the product of the temperature and change in standard entropy. In spontaneous reactions, entropy has to be positive, however enthalpy can be negative or positive. This demonstration shows just that. You can calculate the spontaneity and the increase in entropy. Here you can see barium hydroxide and ammonium chloride being mixed without external energy. The reaction is endothermic as energy was sucked from the surroundings and therefore froze the wooden block to the beaker. Using Gibbs's free energy calculation, we can see that delta G is negative, showing the reaction to be spontaneous. The ratio of the moles change and increase, and the products include a liquid and a gas, in which particles can move around more freely, showing a larger increase in entropy. Using all of this newfound knowledge, we can now see why ice melts, why hot pans cool down, and why warm drinks get colder. As Carnot said, any spontaneous process increases the disorder of the universe, hence entropy is the arrow of time.